Next we will have Larson, who's going to tell us about geometry of Delta-Matroids.
I'd like to start by thanking the organizers for a great conference. Even though most of them aren't here, but I'm going to talk about an algebro-geometric construction related to Delta-Matroids. We saw Delta-Matroids yesterday a lot, but let me fix some notation. So n for me is going to be some positive integer, and I'm going to set n bar to be the set 1 through n together with 1 bar through n bar. So this is just some set of sizes to n equipped with some nice involution that exchanges I and I bar. So yesterday there were stars. So I like bars. Then K is going to be some field. Doesn't matter the characteristic or anything. And I'm going to consider the vector space of dimension 2n, which is labeled by this set. So I'll call that K to the n bar. And then I'm going to consider a bilinear form, a symplectic form of this vector space. Q. And I'm going to take the standard symplectic form. So Q of two vectors x, y is equal to x1, y1 bar plus xn, yn bar minus x1 bar, y1 minus xn bar, yn. Okay, so this is a non-degenerate bilinear form, which is skew symmetric. So it's non-degenerate even characteristic too. And then we say that some subspace L contained in K to the n bar is Lagrangian if Q restricted to L is equal to 0. So it's isotropic with respect to this form. Restrict this form, if I take two vectors in L and I apply Q, I get 0. And it's maximal with respect to this property. So it turns out that the largest dimensional isotropic subspace that you could get is dimension n, so half of the dimension. And so a Lagrangian subspace is just an isotropic subspace of dimension. Okay, so there are some examples. The easiest example is that if I have V contained in K to the n, so any subspace of K to the n, then I can take V direct sum V perp, and I think of this as living inside K to the n bar. So V lives inside K to the n, and then V perp also lives inside K to the n, and then I take the direct sum of them that lives inside K to the n, direct sum K to the n, which is K to the n bar. So this is, it always has dimension n, and it is Lagrangian. So just maybe very concretely, I could take the row span of this matrix as well, which is also of this construction. But here's like a two-dimensional, so this is contained in like K to the 4, K to the 2 bar, two-dimensional vector space, which is okay. So we say that, yesterday we saw the notion of admissible sets.
Sorry. Where's V? So what's V perp? Sorry.
So
where does that lie?
maybe I fix like this, that lives in Kn. So maybe I'm fixing like the standard, bilinear form on Kn, and then V perp lives in Kn, and then I'm identifying Kn, direct sum Kn with Kn and bar in like the obvious way. Okay, so yes.
Is this the only possible way to get a Lagrangian?
No. So yeah, there are many more. Yeah, than just these, but. Okay. Okay. So right. So yesterday we had the notion of an admissible set. So maybe I'll not just say. So an admissible set is a subset of n bar that doesn't contain both I and I bar for any I. So maybe the example is like 1, 3, 4 bar. Contained in 4 bar. So it doesn't have to have size anything. You're just not allowed to have both 4 and 4 bar. Yeah. And then, and then I consider a vector associated to an admissible set, so I'll call it ES. And what you do is you check, so this set, it contains either one bar, or neither. And if it contains one, you put a 1 in the first entry. If it contains 1 bar, you put a -1 in the first entry, and if it contains neither, you put a 0. So ES in this example is 1, 0, 1, -1. So this is in R to the N. In this way, for each admissible set, you get a point in R to the N. And then there's a theorem, which is proved by Gelfand and Serganova in the 80s, which says that if L is a Lagrangian subspace, then D of L, so we can define D of L to be the set S, where the size of S is equal to N, and S is admissible. And the Plücker coordinate is non-zero. Okay, so what this means is you look at all admissible sets of size N. So that's the same as, it's a subset of N bar. So for each I, you have to choose either I or I bar. And then you, maybe you choose, you represent your matrix as the span, the row span of some guy, and then you look at the corresponding minors of this matrix, so the admissible minors, and you check if they're 0. So in this example, this minor corresponding to 1, 2, that determinant of this guy is 0. So that's not in D of L. But if I look at 1, 2 bar, then the determinant of this 2 by 2 minor is not 0. So 1, 2 bar is in D of L. Similarly, 1 bar 2, the determinant of this matrix is not 0. So that's in D of L. But then this 1 bar 2 bar is not in D of L. So in the example, maybe in the example, D of L is equal to, maybe all right, like 1, 2 bar and 1 bar 2. Okay, so they define this set, some set, and then what they show is that the convex hull, or what the statement of the theorem is, that of ES, S in D of L. So this is now a polytope in R to the N, and it has all edges parallel to EI or EI plus or minus EJ.
1, 2. Yeah.
1, 2. So 1, 2 corresponds to this matrix. The determinant of this matrix is 0.
But.
So this example is like.
Okay, label.
Yeah. So right. So the way I label this matrix is like 1, 2, 3 through N, and then 1 bar through N bar. Right, like this is 2 and 2 bar. All right. So in this example, you can verify that here you have 1 minus 1, and here you have minus 1, 1. And then you take the convex hull and you get an edge like this. And okay, theorem is true in this example. This is parallel to whatever EI minus EJ, E1 minus E2. Okay. So maybe I'll call this P D of L. And right, so so I should say that yesterday people talked about if you have a symmetric matrix, then you get a Delta-Matroid. You look at like the principal minors, and the case of the if you have like if you have something like this where A is symmetric, then this is a Lagrangian subspace. And then under some, there's a way to you can identify like subsets. The principal minors of this matrix are going to correspond to the admissible Plücker coordinates of the principal minors of A are going to correspond to the admissible Fluker coordinates of this guy. So
Symmetric means zeros on the diagonal.
no. Yeah. So we also saw you could take a skew symmetric matrix here, and then you also get a delta matrix there. There you turns out you get an even delta matrix or orthogonal matrix, but I want to take symmetric. So if I take a skew symmetric matrix, then it won't be isotropic. I mean, it could be. It's 0 or something. Okay, right. So then I define a Delta-Matroid V is a non-empty collection of admissible sets of size n such that PD, which is defined in this way, you take the convex hull of this polytope, has all edges, convex hull of these, of course, the vertices corresponding to elements of D, has all edges, parallel to EI or EI plus or minus CJ. And this definition, maybe it's not obvious, but, or maybe this was Cynthia mentioned that this is equivalent to the other definitions. Okay, so this is some combinatorial condition that you can consider. And the Gelfand-Sergenova theorem tells you that each Lagrangian subspace gives rise to a delta. Okay, so Delta-Matroids, and Delta-Matroids are via this construction and a combinatorial analog, Delta-Matroids are generalizations of matroids. So if you have a matroid, then there's a natural way to view it as a Delta-Matroid. So this was the lift construction from yesterday. Sort of linear algebraically just corresponds to, if you have V contained in K to the n, you think of that as like a matroid on elements, you take V direct sum V term. So there are, I'm going to consider the independent sets of delta matroids. So I say that some set I is independent and then in D if I is contained in an element of D. So you can think of the elements of D as like the bases of your delta matroid, and being independent is being contained in a basis. It's a reasonable notion. And I'm going to let IK be the number of independent sets of size K. Independent sets of D. Almost ready to state the theorem, but I need one more condition that a delta matrix might or might not satisfy. So we say that D is shelterable. This was a notion introduced by Boucher in the 90s. If there exists a matroid M on n bar, such that for all S admissible, S is independent in D, if and only if S is independent in M. So a delta matroid is shelterable if there's a matroid on n bar, which turns out you can assume has rank n if you want, where if you have an admissible set, you can check whether it's independent in D by checking whether it's independent in M. So usually M will have many independent sets which are not admissible, whereas all the independent sets of D are admissible by definition. But okay, this is a definition you can make. And the reason why this is a reasonable definition is that if D is equal to D of L, so your delta matrix comes from a Lagrangian subspace, then the matroid of L works. So right, being shelterable is about the existence of a matroid like this. So if you want to prove something shelterable, you need to produce a matroid. And if somebody hands you your delta matroid, like it arises from a Lagrangian subspace, then that's right. So you can forget about all this n bar and Lagrangian crap, and you just have an n-dimensional subspace of a 2n-dimensional space, and so you get a matroid. And that matroid, like it certifies that D is shelterable.
Sorry, I didn't understand. Thinking about the bar stuff.
Yeah. So
Because we don't interpret the things like invisible.
so yeah. So
What's the ground?
so the ground set is n bar. So I have a linear subspace of a two.
I didn't read that. I see. It's only when S is invisible in the first place that you're.
Yes.
The if and only if is only after the.
Yes.
Okay.
Yes. Okay. Right. And so being shelterable is quite a reasonable definition, because quite a reasonable condition, or something maybe you would always hope is true, because matroids, somehow they're combinatorial abstractions of linear subspaces. Delta matroids, somehow they're combinatorial abstractions of Lagrangian subspaces. And you know that a Lagrangian subspace is like a linear subspace. And so you would kind of hope that the condition is compatible, but it turns out it's not. There's an example in this paper of Boucher, which he attributes to Duchamp, of delta matroid of 4 elements, which is not shelterable. So, that's life.
Did you say why it's called shelterable?
I guess, so that's his terminology.
Your fault, I know.
I guess it kind of, you have like the independent sets of D, and, they're kind of, out in the cold, and then the matroid is like sheltering.
I know it as envelopable.
So envelopable, if you look at our paper, there are also enveloping matroids. That is a different condition. We don't know if being envelopable is equivalent to being shelterable, but we do know that if I give you a D, and then you can ask, is a matroid, is it an enveloping matroid, or is it like a sheltering matroid? Like, does it certify this? And those are not equivalent.
What is envelopable?
Envelopable is you look at the matroid polytope, and then you project via there's a projection, there's a map n from R to the n bar to R to the n, where you send it goes to xi minus xi bar. And the condition is that m of the matroid polytope is equal to this delta matroid polytope. That's what envelopable means, or to be an enveloping matroid.
What's the Venn diagram that we should keep in mind?
So if M is sheltering, so M is enveloping, implies M is sheltering, but the converse is not true. We don't know, we basically only know one example of a delta matroid. It's hard to check. This is a hard condition to check, because you kind of need to look at all matroids on n bar. And so if D is on 5 elements, then you need to look at all matroids on 10 elements of rank 5.
That I covered your writing. What is the second line?
Where? Here?
The second line of that column.
Second line, xi minus xi bar.
Next line, sorry.
N of P of M equals PD.
What is PD?
PD is the delta matroid polytope, which I defined there. P of M is the base polytope. Yeah, so we only have one example of a delta matroid which isn't shelterable, and it's also not envelopable. But probably they're not the same, but we only have one example, so it's,
Is there a relation between the lift of D and the sheltering matrix
the lift.
of D?
So I should say this. So if D, well, maybe I'll use this notation, lift of M. So what that means, to me, I think about is that it comes from this construction. So you have a subspace and right, there's a Matroid version of this construction. Then lift of n, so Matroid n, then I can take m equal to like n direct sum n per. This is a sheltering. Shelters D. So
Yeah, dual.
dual, yeah. And that's my notation for dual. Okay. Sure, dual. And I only think of vector bumps, so.
You said you didn't like stars.
Yes, indeed, yeah, it'd be too confusing. So, yeah, so for, if you have a delta matrix which arises from a matroid, then it is shelterable. Yeah, so, okay.
One question you said, isn't a counterexample with non-check that will matrix?
Not orthogonal delta matrix.
Yeah. Yeah. Said it's on 4 elements. Does this mean 4 times 2? Or
It's, yeah, it's on 4 bar. Yeah. Okay. All right, so now I can state the theorem. So the theorem has 2 parts. So the first part was proved by Chris, Alex Fink, and Hunter Spink. And it says that, so assume let D be a shelterable delta matrix. Be shelterable. Then the ik squared is greater than or equal to n minus k plus 1 over n minus k times ik minus 1 times ik plus 1. Part 2 proved, I showed that ik squared is greater than or equal to 2n minus k plus 1 over 2n minus k times k plus 1 over k times ik minus 1 times ik plus 1. So this is, if I just ignored these factors, both of these would be saying like log-concavity. These numbers are bigger than 1. So it's better than log-concavity. Yeah, so the if n is close, or if k is close to n, this is stronger because then this is like a bigger number. But if n is like small, if k is small, so if k is like 3 or something, and n is 1,000, then this is going to be better. So these 2 results are incomparable.
Can you express this as like a log-concavity via divided by binomials somehow? Like
You can express it like that. Yeah. Okay, right. And so, yeah, in both cases, the hypothesis of shelterability is needed and is used. So this is the result I am going to talk about. This result is proved, let me just say it's proved using Lorentzian polynomial tricks. And yeah, maybe I could say what this means in the case of matroids. So if D is equal to the lift of M. So again, it's like this. It's this construction of a delta matroid out of a matroid. Then N. All right. Then ik is equal to the number of pairs S contained in T in your matroid. So these are contained in like 1 through N. So N is a matroid on 1 through N. And then the condition is that S is independent, T is spanning, and the size of T minus the size of S is equal to N minus K. So we proved that this sequence associated to any matroid is log-concave, and in fact, satisfies whatever inequality, which I believe is no.
It's proof for this one example, which is not.
Yes. So, so maybe I should say that, right, it's weird that these 2, there's like 2 sort of incomparable statements, and the natural statement would be to remove the 2 here. And that would be like the analog of the strongest version of Mason's conjecture for matroids. And I conjecture that that is true for all Delta-Matroids and not necessarily shelterable. And yeah, and in fact, there are like there's some specific polynomial which seems to be Lorentzian, which would, if you could prove it's Lorentzian, would imply this conjecture. Yes.
If D is lifted, and how does IK related to the number of input process in the matroid then?
So yeah, this is in the matroid.
Okay.
Yeah, so these are independent in the matroid, spanning in the matroid. So n is on the matroid, n is on 1 through n, and then IK like of D. So
Yes, my question is, how is that number related to IK of the matroid M?
oh, this I don't know. Yeah, I mean, probably it's not determined by it. I suspect, you know, but yeah.
What is the support of this Lorentzian polynomial that would imply?
Yeah, can you write this down?
No,
This is hard.
and
Oh, no,
yeah, we can let's talk about it later. Yeah, I wanna focus on this. Yeah. Okay. Yeah, but yeah, so in any case, there's kind of considerable evidence that whatever I'm about to talk about, it works even if the delta matrix is not shelterable, because whatever I'm about to talk about produces sort of complicated Lorentzian polynomials in many variables when the delta matrix is shelterable, provably produces that. And you could check in this one example, and I mean, you could kind of do trivial modifications, like a direct sum or something, and there still stays Lorentzian. So it's some evidence.
One evidence.
Yeah, well, but it's like you can extend, right? So if I take the direct sum with something else, then if I take an extension of this delta matrix, it's still not shelterable. So it's not quite true that there's basically one example, but it's not, there's an infinite family of examples. You direct sum with a loop, whatever.
One question, so typical delta matrix are expected to be shelterable or not?
So that is an interesting question. There is I mean, like with matroids, you expect like a random delta matrix to be kind of simple. So there's a construction of like they're analogues of paving delta matroids. And we didn't try, but Alex said, I don't know, polyhedral or whatever. But Alex told us that it's probably you could prove that these paving guys are always shelterable, in fact, envelopable. I don't know. Yeah. So it might be true, but maybe like a very interesting delta matroid is probably not shelterable. No reason to think it's shelterable. All right. So now I am going to talk about the proof of step 1, which uses some algebro-geometric construction related to delta matrix. So this construction, it takes place on a variety XBN, which is a toric variety of the type B. Yeah, it's the toric variety, and it's the type of the type B permutahedron. BN permutahedron. So a toric variety is associated to a fan, and for like B2, the fan looks like this. So it's, yeah. And in general, the fan is the Weyl chambers of the type B root system. So what that means is you look at the hyperplanes xi equals 0 for each I, xi plus xj equals 0, and xi minus xj equals 0 for each I and j. So that's a bunch of hyperplanes. They cut out some, they cut space into some chamber thing, like here, and then your cones are like the maximal cones are the right. So it's a toric variety, smooth projective, and it has there's a map from xbn to p1 to the n. So you could see that in this picture where the fan of p1 to the n is like this, and then this is a refinement of that fan. And yeah, I'll call this pi equals pi1 through pi n. And what we're going to do is construct some vector bundles associated to at least Lagrangian subspaces on XBN. So sort of like related to what Andy talked about, at least in the motivation-based talk. So the first step is that we're going to consider some line bundles on P1. So on P1, there's the line bundle O of 1, and P1 is a toric variety. And on toric varieties, there's a correspondence between Neff line bundles and polytopes, like Mario talked about. And between like equivariant line bundles, Neff line bundles, and polytopes. And for O1 on P1, it corresponds to the segment. And there are kind of two natural choices for the segment in, R. So you could take there's like the convex hull, the interval 0, 1. That's like a nice segment. Probably my favorite, to be honest. But then there's something that's like, I don't know, also reasonable, which is you could take the segment -1, 0. If that's your favorite, like, I don't know what to tell you, but it's kind of reasonable. And type B, it's like, you're sort of supposed to do things that like involve signs, and like this thing is invariant under reflecting across like the line x1 = 0. So you kind of don't want to. Maybe those are kind of equally good for us. So let's just take both of them. So I'm going to consider a vector bundle M on P1 again. And what it is it's the direct sum over all I and n of pi I upper star. So you pull back both of the direct sum of both of these line bundles. So I'm going to call it O1 sub 0, 1, and then direct sum O sub -1, 0, 1. So this is a rank 2n vector bundle on XBN. Okay. And then I can state a theorem / definition to us, which says that if L contained in k to the n bar is Lagrangian, then there exists unique equivariant vector bundles SL and QL, such that there's a short exact sequence. 0 goes to SL, goes to M. So M stands for middle. Goes to QL, goes to 0. And so this is short exact sequence of equivariant vector bundles. And the fiber over the identity, like of the torus, is 0 goes to L, goes to k to the n, n bar, goes to k to the n, n bar, mod L. Yeah. And the total Chern class of QL, so this lives inside the Chow cohomology of the type B permutohedron, only depends on D. So this is equal to 1 plus C1 of QL plus Cn QL. So this only depends on D of L. And what you do is you compute a formula for this thing, and you check like it's fine in terms of some invariancy Delta-Matroid, and just like makes sense for any Delta-Matroid. And then we define C of QD for all Delta-Matroids.
Any reason to consider non-equivalent version?
So the uniqueness really requires equivariance. So the uniqueness, so I told you what it is over the identity, and then the equivariance means that's going to uniquely determine what it is over the torus. And then M is like, it's well defined. I defined it over there. And I've told you what this vector bundle S, the total space of this vector bundle is over the torus. And so there's a unique thing it could be, which is you take the closure of, what it is over the torus, because the torus is dense. And then you have to prove that that is the total space of a vector bundle.
The existence can fail when L is not Lagrangian.
That's true, yes. Yeah.
So in the definition of do you want the pullback of the vector of the line bundles back to xdn?
Yeah, so pi is a map, right? So yes, you pull back you pull back to P1 and then all the way to XPN. So
Yeah, because it's just that from the way you've written, it seems to be pi I of those line bundles.
yeah, so pi I for me is the map from XPN to the ith factor of P1.
Right.
Here, right? But yeah, okay. Yes.
Sorry, can you explain the difference between O of, so 0, 1 is like a polytope?
Yeah.
And -1, 0, they don't keep the same.
Yeah, so maybe I'll write down what this looks like over the torus.
So maybe, Alan, I would consider O of D zero and O of D one.
It's same or equal, it's just a way.
So
Minus D.
so over the torus, this bundle M, it looks like it's trivial of rank 2n, and the coordinates are labeled by like n and n bar. And if I have t equals t1 through tn, then t dot like x1 through xn bar, it's equal to x1 through xn times t x1 bar through t xn bar. So the torus action is different. And so right, so I said how SL is determined is you look at the fiber of the identity and then you act by the torus. So to tell you what it is at some point t, I act by the torus that moves out. And that's this action is gonna, it's gonna change, right? The fiber, you can still identify it with k to the n bar, but it's because I took two different things here. That's why it acts differently on the n factor and the n bar factor.
This is a pullback of morphism into the Lagrangian.
No, it's a pullback. Yeah, maybe. Yeah, no, turns out it's not. It's a pullback. It's a map into some Grassmannian, which is not the Lagrangian Grassmannian. But
Are these valued or?
they are valued invariants of Delta-Matroids. The Q churn of QD turns out.
Is in the direction of O plus I bar, where I is going from.
Sorry, this is M restricted to the torus.
There's plus is vector extended to plus like I. Should you get rid of that plus there, I guess?
If I wrote this, would you be happier?
It doesn't matter.
Okay. Okay, so all right, so we have some vector bundles, and then fun thing to do is intersection theory. And so a question you can ask, so maybe before I say that, I should say that this is a direct analog of a construction in my paper with Chris and June on stellahedral geometry of matroids, which is itself an analog of a construction in a paper by Andy, Chris, Hunter Spink, and Dennis Sung, on which constructs something similar on the permutahedron. Associate, some vector bundles associated matroids, and there you get a vector bundle of rank n minus r on like an n minus 1 dimensional variety. And so, you have like a vector bundle of rank n minus r, you look at the Chern class and there's like a most interesting piece, which is the top Chern class. And that turns out to the Bergman class of your matroid. So from this perspective, you could like rediscover the Bergman class. A historical, but here we have a rank n vector bundle on a rank n variety. So the top Chern class is just a number. Turns out it'll be an interesting number, but it's just a number. And so you don't really have, none of the Chern classes are more interesting to look at than any of the others. I mean, maybe C0, it's like 1, it's not kind of less interesting, but yeah, unlike in the matrix case, this does not give an analog of the Bergman map. Or maybe it gives like n different analogs of the Bergman perspective, optimistic or pessimistic. But in any case, yeah, so I said, see this top Chern class, it's a number. And what number is it? So it lives in the top cohomology, or top chow, an of xpn. That's canonically isomorphic to z. What is it? Yeah, let me just say this is a really concrete linear algebra question. So suppose I choose A1 through AN, A1 bar through AN bar, and B1 through BN bar, generic. okay, then this number is equal to the number of t in the torus T, such that A1 T1 plus B1 through AN Tn plus Bn, A1 bar T1 inverse plus B1 bar through AN bar Tn bar plus Bn bar lies in T dot L. Where, so yeah, here I have an action of the torus on k to the 2n, so k to the nn bar, where I like scale the last n factors. And so T dot L makes sense. It's like a well-defined subspace for any T. And then I'm asking, if you choose these generic, how many points of the torus does this, element of k to the nn bar live in T dot L? So it's like concrete generic, concrete linear algebra question. Right, so this comes from the fact that the top Turing class for a nice globally generated vector bundle is the vanishing locus of a generic section, number of points in a generic section. And then, okay, but I don't know, at least to me, this seems like kind of hard linear algebra question. And as Matu's taught us, when you're faced with a difficult linear algebra question, you should ask a wizard. And yeah, so you look through this book, and I don't think there's anything that's going to help us here. But luckily, Fulton wrote a great book, but this is just a book. It's not a wizard. Yeah, and my original conception was that I would pull up this board and then the book would be behind it, but there's like a black hole down here. Yeah, so Fulton, he's a great mathematician. He had has a rich legacy, and including he has a great student, Sam. And Sam has taught us a great spell called equivariant localization on toric varieties. And it turns out that spell solved this problem. So the idea is to look at the torus equivariant Turing class of QD. So turns out there's also, so I wrote it like sort of non-equivariantly, but there's a equivariant version of this guy. And then what this is a piecewise polynomial of degree n on the fan of xbn. So for each cone, maximal cone in xbn, I'm supposed to give you a polynomial of degree n, and there's some compatibility condition. So let me, for this running example, I guess from there, let me tell you what it is. So this is the fan of xb2. For these cones, I give 0. For this cone, I put minus t1, t2. So it's a polynomial in t1 through tn, in like the equivariant homology of the torus. This guy I put minus t1, t2, 0, 0, minus t1, t2, minus t1, t2. And what you observe in this example, and it's true generally, is that this is constant on the fan of p1 to the n. So it only depends on which orthant you're in, right? It's 0 in this orthant and orthant. So the answer is pulled back from p1 to the n. And that just means that it's constant on each orthant. And so the value on an orthant is 0 if 0 or plus or minus t1 through tn, binomial t1 through tn. And the plus or minus just corresponds to some like weird convention. So they all, you should ignore the plus or minus part. But whether it's 0 is determined by whether or not some particular set is a basis of your Delta-Matroid. So in this example, the fact that 1, 1 is not a basis means that this is 0. The fact that -1, -1 is not a basis means that this is 0. The fact that the other two are bases means that these are 0. And then you can, P1 to the n is kind of simple. And you just like count the number of orthits for which you get like not 0. And so the answer is that this is equal to the number of independent sets of size n of your delta matrix, the number of bases. Okay. So any questions about that? Didn't fully explain it. Yeah. Here's
You're computing the equivalent localization in two ways, right?
Sorry?
You're computing the equivalent localization in two ways. One where the zero locus of the section and the other one. Since this gives like this equality.
So I'm just saying I'm computing, I write down a formula for this. I observe that it is pulled back from P1 to the n. And then P1 to the n is just a simple torque, right? So in general, if you have a piecewise polynomial, figuring out what the degree is, there's an algorithm, but it's like kind of complicated. But in this case, it's pulled back from P1 to the n, which is just a very simple torque, right? And can just read off immediately what the answer is. Okay. All right. So that's the top trig class, and then yeah. What about the other trig classes? So let me define yn as pi n upper star of the class of a point. So this is right. So pi n is a map from xpn to p1, and then I take like O of 1 on P1, which is the same as the class of a point. I pull it back and I get some divisor class. So this is in A1 of xpn. And I want to compute what yn times, so this is degree 1. I want to get something of degree n, Cn minus 1 of qd is. So this is going to be a number. It turns out that yn, yeah, so there's yn is the class of the closure of a subtorus inside xpn. So this is things of the form t1 through tn minus 1. So yn is like, on the torus, it's like fixing the last coordinate. It's telling you the divisor, to compute the divisor, you fix the last coordinate. And yeah, yn is this closure. And then this, the closure of gm to the n minus 1 is isomorphic to xbn minus 1, turns out. It's isomorphic to a smaller type B primitive. So in the, yeah, so there are also like, this is not a torus invariant divisor on xbn, but it turns out there are these sort of weird intermediate guys that like aren't fixed by the torus, they're fixed by this codimension 1 subtorus that sits inside xbn. And then if I look at, chapter 8, in here, then, yeah, then it tells me that when you're integrating the class of a subvariety against another class, that's the same thing as restricting this class to that subvariety and then integrating. So this is equal to the integral of x bn minus 1 of cn minus 1 of qd restricted to x bn minus 1. And then this thing is it's equal to the top turn class of a different delta matroid, which I'll say what it is in a second. So I'll call it d of n. So d of n is the delta matroid whose bases are the independent sets of D which don't contain n or n bar. So you look at, there are a lot of independent sets of D. You look at the ones that don't have n or n bar. So the maximal size of these is n minus 1. And that gives you a family of subsets of n minus 1 comma n minus 1 bar. And it turns out that those are the bases of a delta matroid, which I call d of n. So this is one way in which delta matroids are nicer than even delta matroids, because if your initial delta matroid is even, this is not going to be even in general. But that means that I know how to compute it. This is the number of independent sets which of D which do not contain either n minus 1 or either n or n bar. So generalizing this construction, what I get is that if I multiply y1 plus, if I sum the yi's, so yi is now the closure on pi I upper star, right, of Cn minus 1 of Qd, then I get In minus 1. Because an independent set of size n minus 1, there's a unique element that it doesn't contain, unique element I, where it doesn't contain either I or I bar, or some I, because it has n minus 1 guys in it, so it hits minus 1 of them. And then each of those will show up once. And then if you generalize this computation further, then what you get is, if I integrate y1 plus this to the k times Cn minus k of Qd, then I get k factorial times I n minus k. So I figured out how to intersect the total Chern class of Q against powers of the yi.
That was a question.
All right, so that's some computation, which opinions may differ on whether or not it's interesting, but I will explain about why this helps you prove log-concavity. So the way people prove log-concavity using intersection theory is that there's this Khovansky-Tessier inequality, which says that if you have two NAF, so two sort of positive divisors, and then you look at their mixed intersection numbers. So you raise one to some power, and then you raise the other one to like the complementary power and take the degree. That gives you some sequence of numbers, and then that is a log-concave sequence. That's what the Khovansky-Tessier inequality does. Here, we're integrating the Chern class of a vector bundle against some divisor to some power. So the divisors and power part, that looks good, but the Chern class of vector bundle part, that's not quite what it says. But it turns out you could convert it into the other way, into a good situation. So we have this surjection, ML goes to QL goes to 0. And then there's this ML, it's just a direct sum of pullbacks of O of 1. And O of 1 is a globally generated vector bundle. So there's a surjection from like O to the direct sum 2 on P1 to O of 1. And then if I combine these all together, I get a surjection from O to the 4n onto ML, because I have 2n O of 1s. And then that surjects onto Q. And then I can take the kernel. I'll call that KL. So this is a vector bundle. KL is a vector bundle of rank 3n, and it's contained in O to the 4n. And then I can look at the projectivization of KL over XBN. And this sits inside the projectivization of O to the 4n over XBN. So it sits inside XBN times P to the 4n minus 1. And then if I look at chapter 3 in here on segregated classes, then what it tells you is that if you integrate on P of KL of y1 plus yn to the k times the hyperplane class from here to the 4n minus 1 minus k, so the complementary dimension, then this is equal to the integral on xbn of y1 plus yn to the k times c n minus k of ql. And then this is equal to, we just computed, it's n minus k factorial times the k factorial times the number of independent sets. So what this does is it realizes this intersection number as you're intersecting two divisors to various powers. And then this is exactly what the Khovansky-Tessier inequality tells you is log-concave. So this implies log-concavity for realizable L. So for D equals D of L. Any questions?
First inequality.
The first inequality, yeah. So I'm not going to talk about the other one. Okay, but then, I claimed that it was true for all shelterable delta-matroids, right? And there are non-realizable delta-matroids that are not shelterable. So if I take a non-realizable matroid and do this lift construction, then I believe it's never realizable. And so you can reformulate this further as, so for any delta-matroid D, you can write down, define a class P of, which I'll call P of KD inside the cohomology or chow of xpn times P to the 4n minus 1. And then, right, so if D is realizable, then this class is just going to be the class of the projectivization of K of L. And then, you work hard and you write down a formula for that class, and then that formula just makes sense for an arbitrary delta matroid. And so that's how you define this. And then we still have this formula, we have an analog of the formula before, where now we're integrating over xpn times P to the 4n minus 1, where you integrate P of KD times y1 plus yn to the k times h to the 4n minus 1 minus k. And then this is still equal to k factorial times in minus k. And in order to prove log-concavity, what you need to know is that this class has like good Hodge theoretic properties. So this is sort of exactly what the situation was for Matroid circa 2012, where you had some formula like this that intersecting in the permutahedron, and if you could prove that the relevant class had good properties, then you could prove the log-concavity characteristic polynomial. But this class is just defined in a combinatorial way, and so it's unclear how to prove, I don't know anything about it. Well, any sort of positivity property balance. But it turns out that, so when D is shelterable, what we can do is we can relate P of KD to the Bergman class of the corresponding matroid. Of a matroid, which is the shelter matroid. And then we can use a result of Ardella-Denham and to prove good properties for K of D. So this strategy was introduced in the paper by Burgett, Eur, Spink, and Son. But for just like a random delta matroid, there's no like nice matroid that you can relate it to, at least in a way that's good for doing this. And so you can't really use this strategy for arbitrary delta matroids. It's sort of somehow intrinsically delta matroid construction that doesn't have anything to do with matroids, it appears. And so for general matroids or for general delta matroids, this log-concavity is just a conjecture. I'll end that.
You have some band associated to D.
For P of KD.
It's like a balanced band.
That's right. It's not uniquely balanced.
Not uniquely balanced. Even when D is shorter.
It's basically, it's like a sum of non-negative things by construction. And so, it's like never the balanced.
Some idea what to do.
Check back in a year or two.
When you do the integration using a total localization, you may get some terms which involves equivalent parameters before truncating those parameters? Is there some combinatorial meaning for the other terms?
So you mean if I do this integral t equivariantly?
The upper one, the top chunk, yeah.
Yeah, so this, I mean, this is a degree n, so when I push forward, I land in h0 of the.
Yeah, but the torus equivalence child of the point, right?
Yeah, but it's h0, so it's just a number. So this does not have an extension. This is really just a number, yeah, even at torus equivariant.
But you can get the number of the sum of the.
That's right. So you can use the Atiyah-Bott localization theorem to write it as a sum of rational functions. Yeah, we did not have to do that. We had, right? So because it's pulled back from P1 to the n, and P1 to the n is pretty simple, you can just recognize what it is. It's a Atiyah-Bott free paper, as all my papers are. Yeah.
What happens if you do S and D? And so like, what's the top churn class of that? It's some dual thing.
Yeah, so we have much more general intersection formula. So this somehow you can compute using standard techniques, but we have like much more general intersection formula that requires some ingenuity to compute, where we intersected all of the positive things that we could think about. We get some Lorentzian polynomial on a bunch of variables, and it's yeah, and it's you get like a we know what the answer is. It's somewhat some delta-Matroid invariant, which is known in literature. Yeah, and we can prove some log-concavity.
So what's the Schubert variety of Lagrangian subspace? I mean, it should be the projection of your K of L to the P to the, or well, some affine cone over it should be, or some cone over it should be the projection of that thing to P to the 4n minus 1.
Yeah, I don't know. I mean, it's a little bit less natural than what you're doing, because this KL is like kind of big. You know, it's not rank n, it's rank like 3n. So, but reasonable question.
Yeah, the fact that you're getting like the bases there, that's like direct parallel to what happens with the Schubert.
All right, so there's more questions we can ask if Matt or Coffee will meet again 4:30. Let's thank Matt again.